Hello, students. Very good morning to all of you. So, as of every day, we shall start our quiz now. And as you know, it is the duration of 10 minutes. So try to submit it within 10 minutes. However, I used to provide buffer time, but please try to submit it within the time. Okay, within the time limit. Let me send it to you, and after 10 minutes, we shall start our quiz. I think you have already received it. Have you received it? Yeah, good morning. Have you received the quiz? Please check. Please check again in the classroom, Google Class. Yeah. So please start it and try to finish it on time. Well, let's start the class now. Please try to submit your assignments within the given time, whoever are left till now to submit them. Okay? So, I'm starting today's lecture. Let me share my screen first. Are you able to see it? Okay. Uh, Now, let's start the discussion. If you remember, till our last lecture, whatever we have discussed is that we have discussed about something that is called additive rewards. That are called the finite horizon and infinite horizon. Now, today we shall start that as we have already discussed that how the reward functions are there and how the uh, policy may change based depending on the reward function or the reward value that you are going to assign, and how can the how the entire thing is dependent on the reward functions or the reward value of each state. Okay. Now, what we are going to compute is that what is the ultimate reward or ultimate utility, okay, ultimate utility of a sequential decision making system. Now, say there are n number of, or if, as we are dealing with infinite horizon, so there could be some certain number of steps that I don't know, states, but the fact is that uh, there are there are two ways, okay, there are two ways of assigning utility to preference. Now, how that utility be assigned? The first technique is called additive additive reward. Okay, what is it? It is actually, as we know that there are different states starting from S1 to to it, and it goes on. Therefore, the utility of those sequence of states could be computed using the following equations, that is S1, S0, S1, like that is equals to R of S0 plus R of S1 plus. So this is how the additive reward is being computed. Okay, this is how the additive reward is being computed. That is, you are just summing up the rewards not only for the present states. Present state is S0, and also for the future states, that is S1 onward. Okay, so you are adding up or summing up all the rewards and defining the utility of that sequential decision making system. Okay, so this is how you are going to define the things. Now, then comes another way of representation. This is additive reward, and the another way of computing the utility of the sequential decision making system is uh, well, Mr. Aditya, now I am, since I am discussing the topics, I shall check it later on. Okay, I shall check the last question later. Now, the fact is that the other way of Computing the utility is discount reward. Discount reward. Okay. So how that could be represented? It is the, well, let me copy it. Copy the equation first. This this left hand side is going to be the same, that is we are about to compute the utility of that sequential decision making, but here instead of this equation changes like then so this equation is changing down to this one. That is, here we are adding a factor as gamma, okay? And that weightage is being assigned. And this gamma should lie, the value of the gamma should lie between, that is 0 that is the value of gamma should lie between 0 and 1, and the term gamma is known as discount factor. It is known as discount factor. Discount factor is gamma and it should lie between 0 and 1. Okay. So this is what is called decision discount factor. And what does it physically signifies? It physically signifies, what does it physically signifies is actually that it describes the preference of the agent to the current reward. That is, if gamma is equal to 1, then what the situation is? Then you are giving equal preference from as well as that of the current reward to all the future rewards. So if gamma is equals to 1, that discounted reward will boils down to additive reward. Therefore, additive reward is a special case of discount reward. You can say that. Okay. When gamma is equal to 1. But when gamma is close to 0, okay, when gamma is close to 0, somewhat close to 0, then what will happen that you are giving highest weightage to the reward of the current state. That is, you are giving highest weightage or assigning highest weightage to RS naught. That is the reward of the current state. And you are almost ignoring the near futures. That is, if gamma is very close to 0, then gamma square, the value of gamma square will be less. Then since it goes on like gamma cube, gamma to the power 4 and like that, so the values of that factor is going to be less and less. Therefore, after some terms, after some rewards, for example, after RS3, the rest of the values will become ignorable. Okay. So, well, Mr. Bharat, I am going to check it. Okay. It must be some mistake that the date is showing to be 10th October. Anyway, the discount factor, that is that we were discussing that if gamma is equal to 1, it boils down to additive reward, and if gamma is close to 0, then you are assigning the highest weightage to the reward of the current state, and the future states or the near future states are almost ignorable, becomes almost ignorable. Okay, so discount factor is equivalent to you. We can see that discount factor is equivalent to interest rate. Interest rate. How the interest rate can be computed? Interest rate is actually, we can say it to be 1 by gamma minus 1. So this is what we treat to be interest rate. This is the interest rate we know, and interest rate is actually equivalent to our discount factor. Okay, so this is the thing that we have discussed. Now, the fact is that if the environment does not, what will happen if the environment does not contain any terminal state? Then the environment history is going to be infinitely long, and if you assign some additive reward to it, then the total amount of reward is going to be close to plus infinity. Okay, so what will happen if no terminal state is there? Then what will happen? What is going to happen? Then if you are assigning some additive reward, and the additive reward will anyway boils down to plus infinity. With additive reward, you are going to have a utility of, additive reward is going to gives a utility of plus infinity. Anyway, we are going to have a utility of plus infinite. Okay, this is what you are going to have with additive reward. But please remember that this is never desirable. Yes, plus infinity is more desirable compared to minus infinity. But to have an utility value equivalent to infinity is never desirable for any decision making system. Okay, and therefore, what could be the solution? What could be the solution against it? Solution. So, what could be the solution? The first solution could be, as we have discussed, one of the solution, that is adding discount factor or having discount factor. So with discount factor, how we are going to handle it? Let's see how we are going to handle it. That is, with discount factor, our values are going to be like is 0, is 1, like that, is going to be equals to sum over t comma to the power t r max r max equals to, hello, am I audible to you? Okay. Then it is going to be equal to gamma to the power t into r of s t. Okay. So this, where t will vary from 0 to infinite if there is no terminal state there. Okay. Now, as we know, it should definitely be less than or equals to that factor, that is summation over t r max, that is the max value, gamma to the power t into r max. Okay. So if the sum of the reward value, that is the maximum reward value among all those given RST, so if you sum it up, this term should definitely be less than or equal to of this term. Now we know this is a fixed, that is a fixed point, or it is a constant. R max is going to be a constant, and if you sum it up using the law of infinite GP, it will give you the result to be R max R max divided by 1 minus gamma. So this is what we can conclude, that even though there is no terminal state and the sequence is infinite, the utility of the sequence could be boils down to a finite number, that is R max divided by 1 minus gamma, if we use discount factor. Okay. So is this much clear to you? Is this much clear to you? Hello? Okay. Thank you. What kind of derivation you are looking for? For which you want to have a derivation? For which term? if you if you are asking me how this summation is being done, this derivation you have already done in your 12th standard. The summation of infinite geometric progressive series. Okay, this is that formula only. Infinite geometric progressive series, how to sum it up with, that is how the summation could be done. That part is already done in your 12th standard mathematics. Okay, so now what is the second factor? Okay, so second solution, first solution is discount factor. Second solution is that we should have a policy that guarantees us to reach to a terminal state. Therefore, the second solution is that policy that guarantees to guarantees to reach a terminal state. Then there will not be any infinite number of states present. Okay. So that type of policy that guarantees us to reach a terminal state is termed as to be a proper policy. Okay. So that policy is known to be a proper policy. Here we can use additive reward also. But if we are having some improper policy, that is where no terminal state is present there, we shall call that policy to be improper policy, and for improper policies only discounted reward or discount reward should be used, no additive reward should be used. Okay, so then comes the third way of solution. Now, here another way of solution is that is, since you are given with an infinite sequence of states, it could be compared in terms of average reward to obtain per time state. Okay, so what we are going to have to obtain, that is, we are going to obtain the average reward, and we are dividing out that infinite time series to be some finite, to be combination of some short finite time steps. Okay, and we are computing the average over that finite time steps, and we are computing. Okay, for example, that sequence of states that I have shown you in the previous class, if for the position 1 1 we are having a reward that is equivalent to 0.1, and we are assigning the reward for rest of the states except those exit states to be 0.01, then the policy will always divert the agent to be in the state that is 1. Okay, so this is the fact, that is infinite sequence. This is the third solution, that is infinite sequence can be subdivided into small steps. Okay, so this is the third solution that we can have. Now here comes that the relation between optimal policies and utilities of the states. States. What is the relation that exists between these two factors? Okay. Now, say we are having a state That is, we assume that our initial state is to be S, and ST is a random variable that the agent reaches after executing the policy pi. So we have a policy, we have a starting state, and we have some random state that the agent encounters after executing the policy pi. Okay. Now let's denote that the initial state to be, let's denote that S is 0 is the initial state. Initial state, or the agent now is now. Agent now is in. Okay. S0 is that state, and the probability of distribution over the state sequence is determined by the initial state S and the policy pi and the transition model of the environment. As we know, we are dealing with MDPs, we should always have this information with us. That is, we should always have the initial state, the information about the initial state. We should have a policy and we should have the state transition model. Now, the fact is that if we are going to compute the expected utility by executing that policy, how we are going to compute the expected utility? That is XPU by executing pi that we are going to compute, and that is actually denoted as U pi is. This is how the utility of the state is after executing over the policy pi is being denoted. That is U pi x. Okay. And it is the expected value of sum over t t t varies from 0 to infinity. Now, comma to the power t r s t. Okay, so this is how the expected utility is being computed. That is, gamma varies for t varies for 0 to infinity, and we are computing that entire amount of reward or the total discounted reward of that function, and we are taking the average of it or expected value of that total reward. Okay, so this is how the utility of that policy with respect to that particular state S is being computed. Okay, over a state sequence is being computed. Now, is determined by S and pi. Now, the fact is that if we are having the optimal policy, once we are going to have the optimal policy, then how does it change? How can we represent it, that what the optimal policy is? It is the expected value not of discount factor, it is the expected value of discounted reward, not discount factor. Discount factor is gamma. discounted reward is that summation. Okay, so this now the fact is that is uh, the in the optimal policy, the how can that optimal policy being computed? The optimal policy that is denoted by pi star s is equals to r max over pi u pi s. So over all the possible policies, we are computing on that utility for each policies on the state, and the one that is going that is that policy that is maximizing that expected utility is to be treated as the optimal policy. We have already discussed in our last class also that what is called the optimal policy, and here we have just described that description mathematically. Okay, I have discussed so many things about discount rewards. Did not you get it, Mr. Aditya, or did you get disconnected? If you get disconnected, just listen to the lecture once again, and you should have an idea about discount rewards. Do you have any confusion, whatever I have discussed so far regarding discount rewards? So now the fact is that discounted utilities with finite horizon is the depends on the optimal policy that is independent of the starting state. That is, if we are computing the discounted utilities in the finite horizon, then the optimal policy that we are going to have is independent on the starting state. How? Because say we are having some optimal policy, say that is denoted as pi star A, that is, say we are having some optimal policy being denoted as pi star A. As you know, this policy means that optimal policy when the sequence is starting from the state A. Okay, but that is in the same universe or same world or in the same finite horizon. Okay, now, this is the optimal policy if the state starts, if that sequence starts from A. Similarly, in the same finite horizon, another optimal policy you can represent as to be pi star B. It is another optimal policy if the sequence gets starts from B. Okay, so if the sequence gets started from B, then the optimal policy is denoted as pi star B. Now the fact is that these two policies should not disagree with each other, since the finite horizon that we are considering is to be the same. Therefore, the transition models or the reward functions are going to be the same. Therefore, that optimal policies be should also be the same for for corresponding states. Okay, so these two optimal policies should not disagree with each other or any other optimal policy. Any other optimal policy could be there. Okay, for example, any some other optimal policy, like there could be another optimal policy, that is, say, pi star c. Okay, now since all of those optimal policies belongs to the same finite horizon, and just the beginning states varies are different, therefore all the optimal policies should be the same. Therefore, for a single finite horizon, there should be a single optimal policy, and that is denoted as to be pi star. Okay, so this is how the optimal policies are actually independent of the starting state. Okay, now the fact is that the true utility of a set, that is determined by the true utility of a set of a state true utility of a state is equals to is denoted by this notation. Okay, that is expected sum, and it is equivalent to expected sum of discounted rewards after executing that optimal policy. So here you are going to execute the optimal policy, and then you are going to compute the expected sum. Okay, like this. You know that this equation from this, and instead of any policy, you are going to execute the optimal policy. Okay, so now as we know that RS, we have already discussed a number of times about RS, that is the reward function. We are now again discussing about another thing, that is US, and it is the utility function. Now, what is the difference between these two? RS actually, that reward function RS, that is represented or denoted by RS. What does RS represents? RS represents short-term reward for being in S. For being in S. Whereas US denotes the long-term reward or total reward from S onwards. Okay, so this is the difference between these two type of utility function and reward function. Okay, so this is this much clear to you? Now let's see an example. Let's see this example. Where is the example? I don't know where does it go. Anyways, I don't know. Some problem might occur here. I don't know what the problem is. Anyways, yes. Yes, this is the example. The same block, and you can say that we have assigned some preference or some utility values to each of the blocks. Now, the fact to be noted is that here the utility value is maximum and it is 0.918 because it is close to plus 1, and being that state, the agent is quite likely to enter to plus 1. Okay, whereas the utility value is minimum of this state, since it is very close to minus 1, and it is quite likely that the agent may end up being in minus 1. Whereas for these states, the utility values are less than even that starting state. Why? Because for these states, entering into minus 1, the probability of entering into minus 1 are quite high. Therefore, the preferences for these states are set as in this manner. Okay, the utility values there, those are assigned is uh, set in this manner. Okay, so is this much clear to you? Is this much clear to you? Mr. Aditya, if you are facing any problem understanding the things, you may write to me, okay? Because I don't have sufficient time to repeat the things again, okay? So you might be facing some difficulties in understanding the things. You may write to me, okay, with your doubts and queries. I shall try to clear it. Now, is there any doubt whatever I have discussed so far? Anyone else? Do you have any doubt on it? Then I shall proceed. Now, the fact is that the utility function of a state, it allows the agent to select the action by maximizing the expected utility. Okay, maximization of expected utility. Now, the agent will always choose the action that maximizes the expected utility. So that's why we have assigned minimum utility values to these states and maximum utility values to these states. So that the agent being here should follow this path, since this path maximizes its expected utility. We can compute, and that's what we are going to discuss now, that how to compute those values. Okay, and this is a very vital part that we are going to discuss now. It is called value iteration, how we are going to compute the values of utilities. Value iteration. Now, as you know that we are supposed to calculate an optimal policy, and we need to calculate utilities in each state and use state utilities to select an optimal action in each state. Okay, now the fact is that how to do things. Okay, how should we do the things? Now, this is the fact. Therefore, there is a very important equation that is named as Bellman's equations. Bellman's equation. Bellman's equation is there, using which we can compute the utilities. So Bellman's equation for utilities does exist there. How does utility is being computed using Bellman's equation? Bellman's equation is used to compute the utilities as utility of the of a state. According to Bellman's equation, it is the immediate reward of immediate reward for the state that plus it should be summed up with expected discounted utility of the next state assuming the agent will select the optimal action. Agent will select the optimal action. This concept is known as Bellman's equation, and now we are going to write down it mathematically. How can it be written down mathematically? How? It is U of S, utility of a state, is equal to reward for the state, that is RS, plus discount factor gamma into max gamma into max over A max over this. Now sum over is P of S bar over S comma U S. S bar is the next state, you know it. And this is the transition model, you do already have it. And you have a set of actions. It is denoted as AS. You have to take that action that is maximizing this term. Okay? You have to choose that action that is maximizing this term, and you have to multiply it with that discount factor. Okay? And this is how you are going to compute the utility of a state. Now, let's again consider the example that we have shown in our last class. Well, for the sake of simplicity, I think we should draw that box here. Okay, we should draw the box here. Here, let's draw the box again. Let it be here. Let it be here. Now, over that, if we want to compute the utility of the state, let's try to compute the utility of the state on. How should we compute? We know the discount factor or the reward function here is minus 0.0. Okay, that should be that should be summed up with the discount factor gamma, and gamma should be multiplied with max of Now, that is the interesting thing. You are computing it for this block. There could be there could be four possible actions. That is up, down, right, left. Okay. For the agent, it has four set of actions that it can choose: up, down, right, left. With optimal policy, as we know, according to our transition model, the probability of going up is zero point 0.8. The probability of going right or left is zero point 0.1 and 0.2 for the action up. Okay. So with respect to the action up, it has 0.8 into u 1 2, because with 0.8 probability it can reach to the block 1. Okay. It should be summed up with 0.1 into u 1 1. If it goes to left, it will remain in the same block, and it has the probability of being in the same block of 0.1. Similarly, it also have the probability of 0.1 to reach to the block. What? Can you say? U of what? Can you say what? I have already taken that fact into account. There is another block it can reach. To which block? It is 2 1. 2 1. It is this block. With 0.1 probability, it can also reach this block. So this is one turn if up is the action or up is the intended action. For the intended action up, this is that this is what the issue could be. Okay, this is for up. Now there comes another possibility. It is that now it is heading or its intended action might be going to say left. Left is the intended action that it is having. Okay. As we know, it has four set of actions, and any one of it could be its intended action. So if left it is its intended action, then for left it will have zero point 0.8 probability of being in the block 1 1. For if for down also it will have the probability of being there in the block 1 1 also too. Therefore, the for intended action left, the utility, this is going to be the utility. Okay. So with and 0.1 of being there into 1. This is for action. Let's mark it. This is for against action up. This is against action left. Then there comes two more intended action. That is, one is down. For down also, the probability of being there in block 1 1 will remain plus this is for going to down. This is the intended action. This is for the intended action down. There comes another action, that is right. For right, what is going to be the fact? That is, then there is 0.8 probability of being there in 2, 1, plus 0.1 probability of being there in 1, 2, and plus 0.1 probability of being there in 1. So this is for the intended action right. So you have to take the maximum value among these 4 possible actions. You have to maximum the value and you have to choose that utility values, that action that is maximizing that utility. Okay. Now, if you compute everything, you will see that here up is going to be the optimal action. Up is going to be the best action. So, is this much clear to you? Then we are again going to discuss about the algorithm, how to compute these values and all those things. But is this much clear to you? No response from your end. Can you hear me? Yes. Okay. Now, the fact is that then we are going to discuss the algorithm that is called value iteration. Value iteration algorithm. Now, as we have seen in Bellman's equation, for example, we have n number of states. For n number of states, we are going to have n number of Bellman's equation. So, if we don't consider again anything else, then from linear algebra, we can conclude that if we have n unknowns and n number of equations, n number of different equations, we shall be able to compute or to find out those n unknowns, the value of those n unknowns. But here the fact that we have to note down that the Bellman equation is not a linear equation. Here it is using a nonlinear operator like max. Okay, max is a nonlinear operator. It is not working in a linear form. Therefore, we can't solve it with linear algebra. Okay, due to that max operation, since it is a nonlinear equation, we can't solve it uh, with linear algebra. Rather, what we need to do now, we need to use a iterative approach. Okay, we need to have some iteration to find out or to come up with some optimal values. Okay, therefore, what we are doing, we are first assigning some arbitrary values to each utility, to the utilities of the states. Randomly, we are assigning some arbitrary values initially. Then we are computing, then what we are doing, we are computing this right hand side of the equation. Then we are assigning it to the left hand side. Then we are updating the neighboring utility values corresponding to that US, and that state will be the neighboring state of this or some other. And with that, we are updating the neighboring utility values and we are again repeating this. Okay. So this is how we are going to come. Now, uh, the fact is that let's say we actually denote the ith, well, we denote ui is, it is the utility value of a state is in ith iteration. Okay? So of state is in iteration I. Okay. So this is what it looks like. Now with Bellman's equation, we are using Bellman update. Bellman update is u I plus 1 is equals to, not equals to, is plus max is u is. So this equation is known as Bellman's update equation. That is the same utility value, that is utility value at state is, how it is going to be updated with each iteration. Okay, so this is the thing, that is this is how the updation is being done, and there is the algorithm. Let's discuss about that algorithm. Let's see how the algorithm works. This is the algorithm. Hope you can see. So as you see that the function here is value iteration, and MDP is the input. MDP has S states, action, set of actions A, and a transition model. So these are the given, and reward function and discount factor is also the input. Now this is the error, that the maximum error that you can allow in the utility of any state. And these are the local variables, that is u and u bar. And for each state, we are really assigning the value, the utility value to be 0. Initially, we are assigning the utility value to be 0. And here is another factor, that is delta. That is the maximum change in the utility of any state of an iteration. Okay. Now, initially delta is equal to 0. and u bar is equals to s u. Okay, u bar is assigned to the value of u bar is assigned to u. Now, for each state is what we are doing. We are updating the u bar is using Bellman's update following this equation. If the difference is greater than delta, that is the updated value is greater than the previous value, then we are setting delta to be this difference and we are again repeating the action until and unless our delta is less than this value. Okay, this error value. And once there is very less amount of change in that delta value, then we are returning the u. So this is how you are asking me that how should we compute the value of the utility. This is the algorithm with which you can compute the utility. If you wish, you can implement it, you can test it with the values that is given for in the block. That is, you can test it. Here your discount factor is 1. Your reward values is minus 0.04 for every block except those exit blocks. For every states except those exit states. With these values, and you have a transition model given with respect to your optimal policy. Against that optimal policy, you can check whether you are getting these utility values after executing that algorithm. If you wish, you can check it. Okay? And let me know whether you are getting the same utility values as those are given. Okay? So is this much clear? Is this much clear to you? Okay, very good. So, if this much is said to you, that is why we are we shall leave now, and that is where, and I shall ask you to do some self study. Please go through the rest of that section. That is, please go through this part. Convergence of value iteration and how it is explained, how the convergence is explained. Please do that self study and let me know what the doubts that you are having. I shall start from policy iteration in our next lecture. Okay. So we already have a huge amount left yet. Well, we need to discuss policy iteration, then partially observable MDPs, then game theories. These are the three vital topics we are still left. So please do a self-study over it and let me know uh, whether you are getting the things or not. Okay, so please do it. And let me discuss the quiz now. So this is the optimal policy yields the expected utility to be the highest. This is the first one. In the context of utility over the finite horizon, you know that this is how the finite horizon will look like. Okay. So, in the uh, infinite horizon includes infinite because there is no fixed deadline that you know. Yeah, I have already noticed it. So I shall mark accordingly. Okay, don't need to be worried. Now, what is the policy in a sequence, in a sequential decision process? Those definitions I have already discussed in our last class. Hopefully, you have written it in a well manner because all those definitions were discussed in our last lecture. Now, this example also I have discussed there. That is in this diagram. every block has a reward of minus 0.04. And if uh, if the agent reaches plus one state after 10 steps, what is going to be the utility? That is plus one plus 10 into minus 0.04. That is going to be 0.6. Okay. So now again the fact is that is factor measured by the expected utility of possible environment. Mr. Bharat, I have released the scores till quiz 3. So till quiz 3, you might have received it. Yeah, tomorrow, for tomorrow's quiz, you might, for yesterday's quiz, you might have not received it, but till quiz 3, I have released the score. You must have received it. Now the factor measured by the expected utility of the possible environment history is generated by the policy, and that is quality of the policy, and uh, with that is the life condition is so much pain, the agent heads straight for a nearest exit. Okay. So, well, I think there is some problem with that reward. Here, actually, the reward value is supposed to be minus 1.23. Then the agent will heading for the nearest exit. Okay. So here, actually, the correct option that is given here is supposed to be, with this the correct option is the shortest path towards the, this is supposed to be the correct answer. Okay. So if rs equals to 4, no, rs is not equals to 4, it is equals to minus 0.04. It should not be optimal policy. Where, when now, for which question you are asking that it should not be optimal policy? Factor measured by the expected utility of the possible environment history generated by the policy is actually the quality of policy that we are evaluating. This is how we are evaluating the statement is contradictory for the last question. Contradictory, which statement? This is the shortest path towards, it will take the shortest path. I have already discussed it that it will take the shortest path. With reward value minus 0.04, yes, it is painful. The life is painful, but it is not that much of pain. It will take risk here, but it will not take risk here. Well, this is the policy that is given here. So it will obviously take the shortest path. From here also it will take the shortest path. From here, but being here, from here it will take the shortest path. But being here, it will not put its life in risk. The life is painful, but not that much painful that it should suicide. If it enters to minus 1, then it is equivalent to having a suicide. And if the reward value is more than minus 1, then only it will take that action. Okay. So, anyways, this is, Well, let me check the things again. Okay. So please don't get confused because since my TAs are actually doing the quiz questions nowadays, and there exists, if there I find there is some error against that question, you will be assigned full marks. Okay, so you don't need to be worried because I am checking the questions once again, and if I find any errors there, I shall ask the police to give you full marks against that question. Okay, so you will be assigned full marks against this question number 7. It is supposed to be question number 7. Against question number 7, you will be assigned full marks. Don't be worried. Okay. Okay. Yeah. So no need to be worried of it. You don't need to be worried. Okay. So thanks for attending the class. And if any one of you are having, please go through the book once again also because the things are getting difficult day by day, and you need to have some self study too to grasp the things quickly. Okay? So please do some self study, and I shall upload the assignment today. Please uh, go through it and try to complete it within the day. Okay. Okay. Yeah, I am going to provide you an assignment where there will be some numericals, some programming assignments too. So from there, you can have some sample questions. Okay. So other than that, you are having some quiz, you are having assignments. Similar type of questions will be there in your exam also. Therefore, no other sample questions. And if you still want some more sample questions, uh, then you should practice the exercise that is given in that book. I have already uploaded the book. You should practice the exercise given there. And if you face any difficulty in solving those problems, you should ask. Okay. So for chapter 16, you should start practicing those exercises given there. You don't have the solution. Well, solve it, and if you think that this is not the solution, you can ask me. Because I don't think any ready-made solution is available against that book. I have not seen it. I don't know. Okay. Uh, that is all. Uh, Sunday no assignment. Today I am going to post an assignment. I'm going to post an assignment, and there will be 10 days of time for you to make it complete and submit it. Try to submit it within 10 days because after that given time, the assignments may not be considered in. Okay. Okay. So thank you all of you for, yeah, Nikhil, I have already noticed that, and the time bound is not applicable for it. So that's all for today. Thank you for attending the class. Have a good day and see you in the next one. Okay.